Hey everyone, welcome back. In this explainer, brought to you by Forge College, we're picking up right where we left off in our overview of Solidity data types lesson. Today, we're zooming in on the absolute foundational blueprints of numbers in the Ethereum virtual machine. Look, if you're going to build structural logic on the blockchain, you absolutely have to understand the materials you're working with, right? In Solidity, numbers are literally the concrete and steel of your smart contracts. And trust me, using the wrong ones is a fantastic way to accidentally build a multi-million-dollar bridge to nowhere. Let's make sure that doesn't happen.
Okay, so here's our schematic for today. 1. The blueprint of Solidity integers. 2. Signed versus unsigned types. 3. Why size matters with bit widths. 4. Storage packing for gas. 5. Safety first with checked arithmetic. And finally, 6. Real-world choices. We're going to step through exactly how to pick the right integer size so your smart contract runs brilliantly instead of, breaking catastrophically. Let's dive in. Section 1. Blueprint of Solidity integers, the foundation. So numbers are the absolute bedrock of your smart contract logic. Before you can write any stateful code, you simply have to know how these numeric types behave under pressure. They're your counters, your token balances, timestamps, computed values, the whole shebang. Without them, your smart contract really isn't looking very smart at all. Now, when you're working in Solidity, you've always got to keep in mind the incredibly quirky, highly specific machine you're building for. By default, the EVM rolls off the assembly line handling absolutely everything in massive 256-bit or 32-byte chunks. That's our native word size. You can think of it like a massive standard shipping container. The entire Ethereum infrastructure is basically built to haul these specific containers around as efficiently as possible. So even if you're just shipping a single pair of digital socks, the EVM defaults to giving you this giant 32-byte container to put them in. Kinda crazy, right?
Moving right along to Section 2, signed versus unsigned types, the two flavors. This is actually our first major architectural decision when writing code. You've got to decide right up front whether your variable will ever need to carry the emotional baggage of being a negative number. It's a fundamental fork in the road for your design.
And this divide is pretty straightforward once you actually look at the blueprint. First up, we have int, which stands for signed integers. These guys carry signs, meaning they're fully capable of holding both negative and positive numbers. Then, on the flip side, we have uint, or unsigned integers. These are strictly restricted to holding non-negative whole numbers, so 0 and up. The rule of thumb here? Use uint for things like token balances, because, well, you can't have negative money on the blockchain. But definitely use int for things like a profit and loss delta, where dropping below 0 is actually highly meaningful data.
All right, Section 3, size matters. Bit widths or physical dimensions. Now, the crucial thing to remember here is that when you just lazily type uint or int in your code, Solidity automatically hands you that gigantic 256-bit shipping container we talked about earlier. It just assumes you want the biggest box possible. But you don't always need a massive container for a tiny piece of data, right? Explicitly building smaller containers is actually a huge part of being a solid Web3 developer.
Check this out. Shrinking those physical dimensions from a 256-bit Goliath down to an 8-bit box drastically reduces the maximum and minimum numbers you can represent. A uint 8, for example, only has 8 bits, meaning it maxes out at exactly 255. A uint 16 bumps you up a bit to 65,535. So choosing the right width really means gazing into your crystal ball and understanding the absolute maximum value your variable will realistically hit in its entire lifetime.
Which brings us to Section 4, storage packing for gas, the optimization phase. What's really fascinating about those smaller bit widths we just looked at is how they allow us to engage in every Web3 developer's favorite obsession, saving pennies on gas fees. Since writing to the blockchain costs your users real money, optimizing your physical storage is literally always a top priority.
And that brings us to a beautiful technique known as storage packing. Remember those 32-byte EVM shipping containers? Well, storage packing lets multiple tiny variables share a single cargo bay when they're laid out consecutively in a struct. So instead of paying exorbitant fees for 3 separate shipping containers to move 3 tiny little items, the EVM neatly and automatically packs them all into just one. It's brilliant.
Here's exactly how we engineer that in our code. If we place a tiny ID, like a uint8, and a small flag, say an int16, right next to each other in our contract structure, the compiler realizes, hey, they can both comfortably fit into a single 256-bit slot. Grouping them like this drastically reduces your persistent storage usage, and that translates directly into much cheaper transaction fees for your end users. Honestly, it's an incredibly satisfying optimization to pull off.
But hey, you gotta tread carefully here, because there's a massive catch. Shoving data into a container that's way too small just to save a fraction of a cent on gas? That isn't a clever hack. It is a massive security vulnerability. Let's say a user's token balance is stored as a uint 8, and they receive their 256 token. Well, the container bursts. The value strictly exceeds the physical limits of those 8 bits, and the entire operation completely fails. Not good.
That transitions perfectly into Section 5, Safety First, checked arithmetic, ensuring structural integrity. So what actually happens when a number gets too big for the boundaries you drew? Well, back in the dark ages of early Solidity, if a number got too big, it would silently wrap back around to 0. Imagine a mechanical car odometer rolling over. It was just like that. And this terrifying behavior caused some of the most infamous, tear-inducing hacks in all of crypto history.
Thankfully, those Wild West days are entirely behind us. With modern safety protocols in Solidity version 0.8 and later, an operation that overflows won't just silently wrap around and bankrupt your protocol. Instead, it automatically reverts the transaction. The EVM essentially yanks the emergency brake, cancels all state changes, and throws a loud error to save the day. It is an absolute game changer and a fantastic, sleep-improving safety net for developers.
However, that emergency brake does require a tiny bit of extra gas to continuously operate. So if you're in a hyper-specialized scenario where you actually want wrapping arithmetic, or say you can mathematically prove an overflow is absolutely impossible and you want to squeeze out maximum efficiency, you can wrap your math in an unchecked block. It's basically a danger zone override switch. If you flip it, you better document it heavily because you are actively turning off the compiler's built-in safety features. Proceed with caution.
Finally, we arrive at Section 6, Real-World Integer Choices, the final blueprint. We've looked at all the individual parts, but how do we tie all these schematics back to your actual code? When you're sitting down to write a smart contract, how do you actually put this into practice to build secure APIs for other contracts?
Okay, so here's the playbook. You should always apply a range-first design to pick the safest minimum width. Figure out the realistic minimum and maximum, and build the container to match. Next, keep the default 256 bits for things like array indices and loop counters to avoid unnecessary conversion costs at the EVM level. And lastly, build strict APIs. If an external function shouldn't accept negative numbers, force the caller to use a uint. It acts as an immediate, unbypassable guardrail for your contract that prevents bad data from ever entering your logic in the first place.
Now, as the architect of this contract, you can't just assume everything's going to work perfectly out in the wild. Have you actually stress-tested the boundaries of your ranges? It's literally your job to write robust unit tests that actively and aggressively try to cause an overflow just to ensure the compiler safely rejects those invalid values. Don't just test the happy path. You need to mercilessly test the extreme edges of your integer containers.
Let's do a quick recap of our blueprint today. Respect the strict limits between uint and int. Always remember that massive 256-bit default container. Pack your storage carefully to save gas without introducing explosive bugs. And trust that modern Solidity will safely revert on overflows. Next up in our module, we'll be tackling booleans and logical operations. Until then, I want you to head over to the website, forge.college, to learn more about this subject and tons of other Web3-related topics. And while you're there, ask yourself, what happens to a multi-million-dollar protocol if just one single integer is engineered with the wrong bit width? I'll leave you to ponder that one. Thanks for joining me on this explainer, brought to you by Forge College, and I'll catch you in the next one.